In the supplementary material, it will be presented the main idea of the price-based power management, a method to obtain price response matrices, and experimental results for 9 situations. Let us consider a hybrid system with different sources, loads, and energy storage system. Some questions stand out. First, how can a supervisory control define in real time the operation modes of each source, load, or energy storage element? Second, how can users optimize the system without requiring advanced technical knowledge? And last, how to design a management system that is automatically scalable to different numbers of power elements? One option to manage all these power elements to achieve power balance and energy optimization is to design algorithms based on conventional state machines. However, state machines are usually not scalable solutions. A system with PV generator, battery bank, grid, and different priority loads may have hundreds of states considering battery state of charge, grid energy price, loads priorities, and so on. Also, the state machines are not easily programmed to or set by the user. This research has considered a different approach. Most people know how to optimize money from daily use, so energy interaction between power sources, loads, and batteries have been analyzed as an energy market where the energy is exchanged according to a current energy price. For example, high-cost power generators would produce only when price is high in order to obtain a profit and avoid loss. Considering this idea, we developed a hybrid system where the users can set the system up considering prices, costs, and priorities of all power elements. The management algorithms are automatically generated, and 3 control layers are considered. The first layer is the inner control loop of power converters, which operate as current or voltage sources. The second layer is the power management layer. In this layer, the instantaneous operation mode of the power converters are defined in order to obtain power balance considering the current energy price. And the third layer is the energy management system, which is an optimization layer aiming to minimize costs or maximize reliability. Here we focus on the automatic generation of the second layer, the power management layer. We implement the first and the second control layers to obtain the experimental results shown in the end of this presentation. The power management layer defines the instantaneous operation mode of the power converters and switched elements. Our proposed approach to generate the power management considers that all energy flows through the DC bus. Let us consider a system with PV generator, grid connection, battery energy storage system, and loads. In this system, we can classify the power elements according to their interaction with DC bus. Linear regulator elements here defined are able to linearly change their power with high dynamic response, so they can control the DC bus voltage. Possible operation modes of these elements can be represented by numbers, where the negative signal represents the operation as a load and the positive signal represents the operation as a source. Mode number 0 is the element turned off. We assigned modes -1 and +1 to represent the DC bus voltage regulation, when the power element operates as a linear voltage regulator to the DC bus, changing linearly its power. One example of these operation modes is the battery bank controlling the DC bus voltage as a load, mode -1, or as a source, mode +1. Modes -2 and +2 represent load and source operation with independent power, without direct relation between the DC bus voltage and the element power. In this case, the elements are considered independent current sources to the DC bus. Examples are the battery bank sinking power in fluctuation mode, mode -2, and a PV generator in maximum power point tracking mode, which is mode +2. With these 5 numbers, -2, -1, 0, +1, and +2, it is possible to represent the possible operation modes of the power elements. There are also elements that cannot regulate the DC bus voltage, here defined as not regulator elements. The power of these elements cannot be controlled, or cannot be controlled with enough dynamic response to regulate the DC bus voltage. One example is usual loads, which can only be switched on or off. Not regulator elements can only operate in modes 0 and -2 for loads or +2 for sources. In our proposed approach for the power management layer, the DC bus is considered a marketplace where energy is exchanged between power elements and an inner energy price is calculated. The price is communicated to all sources, loads, and energy storage systems connected to the DC bus. A high price signalizes the low priority loads to turn off and expensive power generators to turn on. On the other hand, a low price means that all loads can be turned on and expensive generators must be turned off. The price calculations consider instantaneous power and energy availability. When energy becomes scarce, price is increased. On the other hand, when there is excess energy, the price is reduced. Thus, an equilibrium point shall be found between price and power demand. Energy scarcity or excess is measured comparing DC bus voltage with predefined values, higher and lower than the nominal DC bus voltage. In order to simplify the algorithm, this price is defined as an integer variable. When the voltage reduces and crosses a low comparison value, this means energy is becoming scarce, so the price is increased by 1. When the voltage increases and crosses a high comparison value, this means there is excess energy, so price is decreased by 1. This way, DC bus voltage is able to signalize the price. In this price-based power management, the price is centrally calculated as a function of DC bus voltage and then communicated to all power elements. While the system is in operation, the power converters and loads are independent elements which define their operation modes comparing the price with their priorities and costs. The selection of the operation mode is inside the PRM block. This PRM block is the price response matrix, explained in the following. A price response matrix is an array which relates different prices with their respective operation modes. The column index is directly related to the price. In this example, the PRM has a single row. At price 0, this power element operates in mode +1. At price -1, it operates in mode 0, and at price equal or higher than 1, the power element operates in mode +2. We can have a relation between the fictitious price and real energy prices considering the concepts of marginal costs for generators and marginal utility for loads. The marginal costs are the additional costs when the production is increased by 1 unit and it's valid for power generators. As an example, the marginal costs of a PV generator is 0 because when its production is increased due to good weather conditions, the total costs do not increase. Therefore, when the energy price is 0, there is no profit or loss. In the price-based power management, we can define that the generators operate in DC bus voltage regulation mode, mode +1, when the price is equal to the marginal costs. For the PV generator, the mode +1 is assigned when price equals 0. When price is negative, the PV generator is turned off to avoid losses, and the PV generator operates in maximum power point tracking mode when price is positive, because it increases the profit. The concept of marginal utility is the increase of total utility or satisfaction when consumption is increased by 1 unit. This is analog to the priority of a load. Different priority levels can be assigned for loads. In this example, there are 3 priority loads: low, medium, and high priority, with different maximum purchase price. When price is increased, low priority loads are turned off, and high priority loads remain connected. In the price-based power management, we can define that the loads operate in the DC bus voltage regulation mode, if possible, which is mode -1, when the price is equal to the marginal utility of the load or the maximum purchase price. When price is lower than the marginal utility, the load can be optionally connected with mode -2, and when price is higher than the marginal utility, the load is turned off. Usual loads can only operate in modes -2 and 0, because their power cannot be controlled. Mode -1 is possible for controlled loads. Another important issue of not regulator elements is that turning on the load when the price is lower than the maximum purchase price is not always convenient. In some cases, this may create inadequate cyclical turn-on and turn-off when total system generated power or stored energy are low. Here, we solved this problem by using number 8 as an indication to keep previous operation mode, -2 or 0, unless changed by the user or the energy management system, which is as an upper control layer. Different price values can also be defined for sources and loads with different operating conditions. For a battery energy storage system, state of charge ranges can be considered as operating conditions. Here, the battery prices for buying and selling energy are split into 3 operating conditions: low, intermediate, and high state of charge. When the state of charge is low, the energy is considered more valuable than in the case when the state of charge is high. Therefore, the prices for buying and selling energy shall also follow this trend. The same idea can be adopted to a bidirectional DC-AC converter connecting the DC bus to the utility grid. When the utility grid has hourly or dynamic energy prices, energy price ranges can be considered as different operating conditions of the DC-AC converter. In this example, 3 different operating conditions were defined: expensive, normal, or cheap utility energy price. Here, the operation mode 11 is shown in the illustrated example. This number means the bidirectional operation -1 and +1 of the DC-AC converter at the same price. This would be valid when the feed-in tariff is equal to the consumption tariff, such as in countries that adopted the net metering policy as an incentive to distributed generation. The user can set up all maximum purchase prices of the loads and minimum sale prices of the power generators, and both for energy storage systems and bidirectional grid connection. The maximum purchase price and minimum sale price are trigger prices, important for the algorithm. Then, the algorithm obtains the internal prices of the price-based power management. The internal prices are integers, 0, 1, 2, that are control signal to access the column of the price response matrices and represent important real prices, decisive to the proper operation of the power management. In this example, the internal prices are defined between 0 and 8, to represent real prices between 0 and 3. A single internal price, here was assigned to a single real price. However, sometimes a single real price can be split into two or more internal prices, and in other cases, two or more real prices can be merged into a single internal price. More details are described in the paper. The next step of the algorithm is to define operation modes inside the PRMs. Let us define the PRM of the photovoltaic generator. The marginal cost of the PV generator is always zero, so it has a single operating condition. In this case, its PRM has a single row. The first step to calculate the PRMs is to assign the internal price 0 equal to the real price 0, as highlighted. Price minus 1 is defined as a safety measure to turn off all power generators when there is an excess energy. The length of the internal price vector, here from minus 1 to 8, is also the length of the PRMs. Here, the operation modes assigned inside the PRM of the PV generator is mode 0, turn off, for price minus 1, mode plus 1, DC bus voltage regulation, for internal price 0, and mode plus 2, MPPT, for internal prices equal or higher than 1. The PRM has multiple rows when the element has multiple operating conditions, so the operating condition can be assigned as the row index of the PRM. Here, the PRM of a battery bank has 3 rows, for low, intermediate, and high state of charge. For bidirectional elements, first the modes plus 1 and minus 1 are assigned to the prices equal to the marginal cost and marginal utility. Then, the other numbers are assigned in ascending order, from minus 2 to plus 2. As an application example of the proposed approach, the power management system was applied to this multifunctional photovoltaic converter with PV generator, battery energy storage system with 3 operating conditions, a DC-AC converter connected to the utility grid with bidirectional power flow, considering 3 operating conditions related to the utility energy price. The system can work in grid-connected or islanded mode. Also, there are 3 loads with different priorities. Assigned by the user, these maximum purchase prices and minimum sale prices, shown in the previous slides, were considered to the elements connected to the DC bus. The algorithm obtained the following PRMs. Loads with different priority levels have different PRMs. As previously explained, number 8 inside the PRM of the loads is an indication to keep the previous operation mode unless changed by the user or the energy management system. In this implemented system, the loads are directly connected to the utility grid. So, when the system is connected to the grid, the assumption that all energy flows through the DC bus is not true. So, the PRMs are only applied to the loads when the system is off-grid. During grid-tied operation, the loads are subjected to the utility grid price. So, the state of the loads is defined by a simple comparison between the utility grid price and their maximum purchase price. In this example, the low priority load is turned off when the utility grid price is expensive because its maximum purchase price is lower than the energy price. No energy management system has been implemented in the prototype, so the turn-on function of the loads has been added to obtain the experimental results. The price 5 was defined to turn on the high priority load, price 3 for the medium priority load, and price 1 for the low priority load. These turn-on prices do not cause the problem of cyclical turn-on and turn-off for low power loads. This is the prototype of the multifunctional photovoltaic converter. The nominal active power of the DC-AC converter is 1.5 kilowatts. Here are the passive filters for each power converter, the DC bus capacitors, the DSP where the control algorithm was implemented, and here are the relays that connect the loads, PV generator, AC grid, and batteries. The PV generator was emulated with a solar array simulator. To increase safety, the grid was emulated through an AC power source. 16 lead-acid batteries connected in series were used as the battery bank. Resistive loads were used for the 3 priority loads. The first test scenario is off-grid operation during the day, with the battery starting with low state of charge. The initial price was defined as 8. In this first interval, the energy is scarce, so the price remains stable at 6, with the battery being charged and controlling the DC bus, mode -1. While the state of charge changes from low to intermediate at the second interval, the new stable price becomes 4, and the high priority load is turned on. In the third interval, the battery achieves high state of charge. The medium priority load is turned on at price 3, and then the new stable price becomes 2. Finally, in the last interval, the battery achieves full charge, so the charging power is reduced to close to 0. So, there is an excess energy in the DC bus, and the new stable price reduces to 0. The low priority load is turned on, and at price 0, the photovoltaic converter stops the maximum power point tracking mode operation and starts operating in DC bus voltage regulation mode, so the system achieves the final power balance. The second test scenario is an off-grid operation during the night, with the battery starting with high state of charge. The initial price was defined as 0. In the first interval, the price is initially 0. The loads are disconnected and the batteries are fully charged. Here, the user turns on the 3 loads. The price stabilizes at 4, and the batteries start discharging, mode +1, controlling the DC bus. In the second interval, first the state of charge changes to intermediate, and then the price rises to 6. The low priority and the medium priority loads are disconnected. Next, the state of charge changes to low, and only the high priority load remains connected. Finally, the battery is completely discharged, and then the high priority load is turned off at price 8. This scenario shows how the system is initialized with high photovoltaic power and the battery is fully charged. The utility grid is disconnected. To assure that all loads are turned off, the initial price is defined as 8. Thus, the photovoltaic generator and the battery supply the energy to the DC bus. When the voltage crosses high comparison values, the price reduces. The loads are turned on at prices 5, 3, and 1. Finally, the stable price is 0, with the photovoltaic converter controlling the DC bus voltage. Now, scenarios where the system is connected to the grid are demonstrated. These scenarios show the behavior of the internal prices with the variation of the utility grid electricity prices. The batteries are with high state of charge. In the first interval, the internal price is initially 3, and the DC-AC converter regulates the DC bus. The price of the utility grid changes from normal to expensive, and the low priority load is disabled. The new stable internal price becomes 4, with the battery selling energy to the DC bus and the DC-AC converter saturated in maximum power, so the battery converter controls the DC bus. In the third interval, the electricity price changes from expensive to cheap. The new stable internal price becomes 1, so the DC-AC converter reverses its power flow and starts regulating the DC bus voltage. Now, the batteries are being charged. This scenario also shows the behavior of the internal prices with the variation of the utility grid prices, but now the batteries are with intermediate in state of charge. Initially, the utility grid price is normal. The batteries are being charged and the stable price is equal to 3. In the second interval, the utility grid price changes to expensive. The low priority load is turned off. The new stable internal price becomes 5, so the batteries stop being charged. The excess photovoltaic power is injected into the AC grid. Now, scenarios where the system connects or disconnects from the utility grid are demonstrated. Here, the batteries are with low state of charge, and the system is initially off the grid. The stable internal price is initially 6, so only the high priority loads are turned on. Then, the system is connected to the grid. The low and medium priority loads are immediately turned on. The DC-AC converter starts working as a rectifier, supplying the DC bus. So, the new stable internal price reduces to 3, and the DC-AC converter starts regulating the DC bus voltage. The batteries continue being charged, but now with maximum power. This scenario is a continuation of the previous one, but now showing the grid disconnection. The batteries are still with low state of charge, and the system is initially connected to the grid. The stable internal price is 3. Then, the AC grid is disconnected. The price rises again, returning to 6. So, the low and medium priority loads are disconnected and only the high priority load remains connected, returning to the original state. Now, the same connection and disconnection tests are carried out with the batteries completely charged. The internal prices are different from the previous situation because now there is surplus energy. Initially, the system is off-grid. The stable price is equal to 0 because the PV generator regulates the DC bus voltage. All loads are active. Then, the system connects to the AC grid. The new stable internal price becomes 3, and the DC-AC converter acts as an inverter, injecting the excess power to the grid. The DC-AC converter now regulates the DC bus voltage, and the PV converter works in maximum power point tracking mode. This last result is the continuation of the previous one. First, the system is connected to the grid with the internal price 3. Then, the grid is disconnected. As a consequence, the stable price returns to 0 and the PV generator starts regulating the DC bus voltage. In this presentation, the price-based power management and the definition of the price response matrices were addressed. To define the PRMs, the user first defines the maximum purchase prices and the minimum sale prices of all power elements connected to the DC bus. Then, the range of internal prices is defined and the operation modes are assigned to the PRMs considering the internal price as column index and the operating condition of the element as row index. The experimental results of a multifunctional photovoltaic converter showed that the price-based power management led the system to an unstable price related to the total energy scarcity. The proposed solution can be applied to bigger hybrid systems where the power elements are connected to a centralized DC bus and the price is communicated to all elements.